Okay, so welcome to the plane curves today. So we had introduced the local ring of an affine curve at a point and shown that it is a discrete valuation ring in a sense that we haven't defined as a term by itself, but if you know it from commutative algebra, you probably have heard it. Otherwise, it means the following. So the setting was that, so recall, say if f is an affine curve, and we have a point P in F, then we had constructed this local ring, which we called OF, P. So the name was local ring or ring of regular functions at P. And the elements are of the form F over G, such that F and G were in the coordinate ring of F, which means they are polynomials modulo F, and such that G at the point P is not equal to 0 in particular, so that we have an evaluation of these things at the point P. And that leads to an ideal inside there IFP, namely all phi and OF, P, that have evaluation 0 at that point. So functions locally around the point that are 0. And that was just the construction. And what we've seen last time is that this OFP, or we can put this in quotes as we haven't defined the term by itself, is a discrete valuation ring. But so what this means is that, so first of all, this ideal inside there, IFP, is principal. It's generated by one element, which we have called T last time. And of course, as a generator of this ideal, it's then determined up to units. And the other thing is that every element phi in the field of rational functions, which we called K of F, which was the quotient field of A of F, that is not 0. K of F star has the form, it's a unit times T to some power. So it's of the form T times T to the N, with T a unit in the local ring OFP, and N is an integer. Actually, it is then the multiplicity of phi as a point, at the point as we've introduced it last time, namely N is this mu P of phi. So that was the result that we ended with last time. And one corollary of that is that we want to start with today is a behavior of this multiplicity here of rational functions under addition. So we have already seen that this mu p is a group homomorphism from the multiplicative group from K of F star to the integers. So meaning when you multiply two rational functions, you add the multiplicities. And if you add two functions, then the following happens. So say let F be an affine curve. And then we say we have two rational functions of phi and psi and K of F. So then for any given point, or P and F, we have the following, that the multiplicity at the point P of the sum of the two rational functions is at least the minimum of the two multiplicities, so of mu P of phi and mu P of psi, where we know that equality holds if these two multiplicities are not the same. So with equality, if, so not if and only if, but it's sufficient to have equality if these multiplicities differ. So if mu p phi is not equal to mu p phi. So that may also something that you've seen in the context of discrete valuation rings and curves. You've seen them before. It's also, it just follows pretty much from that property here. Namely, the way we can prove this is that we say we use, so first of all, we have this expression up there of the form c times t to the n if it's non-zero. So let's first consider the case that one of the rational functions is 0, because then the statement should actually be trivial. So if phi, for example, is the 0 function, then here we have just psi, and here we have the same multiplicity, and this here this was defined to be infinity, the multiplicity, and so the minimum of infinity and the other number is the other number, and so then we have equality on both sides. So first of all, so sort of like the first trivial case, so if the multiplicity mu p, or say if phi is 0 or psi is 0, then we have an equality here actually because on both sides we have the same multiplicity. So the interesting case is clearly the other one. So if phi is not equal to 0 and psi is not equal to 0, then we can write them in this form. And that's what we're just going to do. So that means we know by the above that we can write phi is c times t to the n, and psi is d times t to the m, say, where c and d are units in the local ring, so in O of p, and say one of the two numbers is less than or equal to the other, so say without loss of generality, n is less than or equal to n. Without loss of generality, n less than or equal to m. So if we then add these two functions, so we have psi plus psi, so ct to the n plus dt to the m. Then if n is the smaller number or less than or equal to the other, we can factor this out and write this as ct to the n times and then 1 plus, so we need, so c is a unit, so we can write d over c, and then t to the m minus n, where this m minus n is greater or equal to 0, and that means the function here is actually a regular function, so it contains no negative powers of t. So this element here is actually in the local ring O of p. And if we then apply the multiplicity mu p to that, then first of all it's additive here, so it will be a mu p of c plus mu p, say, n times mu p of t, and then plus mu p of the thing, the bracket on the right, so 1 plus d over c t to the m minus n. And of course, like the first one is 0 because c is a unit, so that one is just 0, and mu p of t is just 1. And the thing on the right is, at least as this is an O of p, this will at least be greater or equal to 0. And so this means this is at least n, and n was the smaller of the two numbers. So this is the minimum of the multiplicities mu p of phi and mu p of psi. So that's just, I mean, it's the same behavior as you would have for power series or polynomials in one variable. So if you have the smallest, so the multiplicity is the smallest non-vanishing term, and if you add those two, then the smallest non-vanishing term occurs at the earliest, at the lower of the two cases when it occurred in one of the polynomials. The equality part is simply if the multiplicities are not the same, then this m is not equal to n. Let me put this in orange here. So if m is not equal to n, what? Okay. What? Never mind. That becomes a unit. Yeah. Actually, yeah. That's what I wanted to say. So if m is not equal to n, then this here is a unit, because that t is then 0 at the point, and you have a 1 plus something, and if it's a unit, this is 0 as well. And so then we have equality here as well. So that's the second part. And so that's in general, I mean, in any discrete valuation ring, in case you know that you would have this property. So that's the thing, how multiplicities behave under addition. What? That is the valuation. So the mu p is the valuation in that discrete valuation ring. Exactly, yeah. Okay. Great. So that's one thing, and there's one thing that we can follow from that, or at least from that whole part that we did here, not just from that. And that is, we can say if we have an affine curve, what actually the regular functions on the whole curve are. So we call this a proposition. That is what are the global regular functions, meaning they are regular at all points. So say let f be an affine curve. Then the following holds if I take the intersection over all points P and F of the local rings, so OF comma P, so they all fit in the field of rational functions in K of F. There you can take the intersection. And that is just another way of saying that's the functions that are regular at all points. So these you would call like global regular functions. Then this is just our A of F. So the coordinate ring meaning K of X, Y over F. So that means, in a sense, the global regular functions are just the polynomials. So you can have nothing in the denominator. That's the statement here, right? So here means we have polynomial functions. And so how do we show that? Let's do the following. So for that proof, I mean, one direction is clearly clear, right? If you have a polynomial function, so that means I can write it without the denominator, then it's regular at every point, right? So that means the direction from right to left. So this inclusion is clear. Every polynomial is regular at every point. So the interesting statement is the other. So if we have a function that is a quotient of polynomials, but I can write it locally around every point so that the denominator doesn't vanish, then it's actually already a polynomial. And so that's the more interesting case. So from left to right. So say we have something on the left-hand side. So say we have phi in the intersection of all these OFP and overall P and F, so a global regular function. So let's consider then an ideal related to phi. So set I be the set of all polynomials. In fact, it will be an ideal. So all polynomials k, x, y, such that when you multiply g with phi, then you land in the coordinate ring, so in A of F. So that means we don't have any denominators anymore if we multiply with g. If we multiply with phi, with that thing, right? So phi can have denominators, but you take all g such when you multiply it with that, then you're in A of F. So that is an ideal, and it clearly does contain f, right? Because if we take f, then, well, f is 0 in A of F anyway, right? Because AF is kxy mod f, and if you take f, then it's 0. So that is an ideal containing f. And we want to use the Nullstellensatz on that ideal. So we're in the case in where we assume an algebraically closed field always, so that's clearly needed for that one, otherwise that will be false. And to be able to use the Nullstellensatz, we want to show that the zero locus of this ideal is actually empty. Well, that's the claim, so let's show that. So we had a similar argument already when we had Bezout's theorem, actually. So let's show the following. So the claim is the zero locus, so V of this ideal is empty. So why is that? So assume not. So say we had a point. Assume P was a point and V of I. Then, first of all, as F is in I, this means that f at the point P is 0. F is in this ideal, so f at the point P will be 0, which means that P is a point on F. And that means it's one of those points, right? And that as phi is in the intersection of all these OFP with P and F, phi will be in this OF comma P, with this P. What this means. phi is an O of P for this point that we found in the zero locus. But that means that I can write it in the form phi is F over G with G of P is not equal to 0. As it's in the local ring. Well, that means G I is F, which is a polynomial. Well, it is an A of F, and that means that this G is in the ideal I. That's how we constructed the ideal. But as it's in the ideal I and P is in V of I, that means G of P is 0. But G of P was not 0, so it's a contradiction to that. So as P is in V of I, it would follow that G of P is 0, and that's the contradiction to the thing here. That was this very similar kind of argument that we had in the case in one of the proofs in the part of the preparations for Bézout's theorem, and shows that this is the empty set, and hence by the Nullstellensatz it means if I have a zero locus with empty, if I have an ideal with empty zero locus, that means that the ideal is the whole ring. So I is the polynomial ring, which means in particular that 1 is in there, and that 1 is in there means that phi is an A of F. So our function phi that we started with on the left-hand side is also on the right-hand side. That's the statement here. So that is already some statement. So it uses clearly with the Nullstellensatz, uses that K is algebraically closed. It's quite already a non-trivial statement, but it looks sort of intuitive, right? So that we cannot have a denominator, because if we had one, there would be poles, and it wouldn't be well defined at those points. Yes, so that's about the regular functions on affine curves. I guess that was it for that part. Yeah. So are there any questions about that? Right here. So if not, well, our actual interest, of course, is not in the affine curves, but in the projective curves. So let's pass already, as we did it earlier for curves as well, now from the affine to the projective case. And so many things will be the same. I mean, everything that's local pretty much will be the same as locally around the point. Everything looks affine, but the global constructions, first of all, are a little different. So we'll have to start with the coordinate ring. So essentially, we go through that chapter again, starting all over with projective curves. And the first thing we did was construct coordinate rings. And for that, so say let F be a projective curve now. So a non-constant homogeneous polynomial in 3 variables. So let F be a projective curve. And we set, now the notation here usually is S of F, and that will be the polynomial ring now in 3 variables modulo the ideal generated by F, and again we call this the coordinate ring of F. Of course, we know already that in contrast to the affine case, the elements in there cannot be interpreted as functions anymore. So in the affine case, we had this remark saying this A of F, which was K of xy mod F, were polynomial functions on F. So here it's not true because it would not be well defined. But we'll make regular functions out of that in a minute, which are quotients of 2 of them of the same degree, and then it works again. So we had the same thing already earlier. when we constructed local ring of the projective space. That's the first thing. We said that. And we actually have f now a homogeneous polynomial, and that sort of means that this ring here is also what's called a graded ring. So I don't want to really introduce like the theory of graded rings, but what we can say is, say we call an element of this homogeneous of degree d, so of S of f homogeneous, of degree d, simply if it has a representative that is homogeneous. So if it is represented by a homogeneous polynomial, degree d, and then we define the S space as D, as index D of F should be the space of all these homogeneous elements together with 0. So say that is 0 together with all homogeneous elements of degree D. Of S of F. So as I said, so if you knew what a graded ring was, then this is actually one. And one consequence of that would be that the SD together form a direct sum to get back S of F, and that's pretty much the only thing I want to show now. It's quite direct from the construction. So a remark is that the whole SD of F, S of F, right, is the direct sum over all natural numbers, all the SD of F. So sometimes when we call this like S of F is a graded ring. Which pretty much means that you have a decomposition of their type and the multiplication with respect to these degrees. So why is that the case? So I guess it's clear that S of F is the sum of all these things, because every polynomial can be written as the sum of homogeneous polynomials. So it's clear that S of F is the sum of all SD of F. And so why is it direct? So say we have a combination of the elements on the thing on the right that gives 0. So say let F0 up to Fn be homogeneous of the corresponding degree. So say degree of Fd is D for all D, such that their sum is 0 here in S of F. So F0 plus F1 plus and so on up to Fn is 0 in S of F. So then we have to show that all the Fd are 0. That means the sum is direct. And so what does it mean in S of F? It's 0. It means that in the polynomial ring, it must be a multiple of F. So that means F0 plus F1 up to Fn is some G times capital F for some polynomial G. And if we now just split the degree part out of that, so say we take only the degree D part of that equation, and if each Fi is correspondingly homogeneous of that degree, then on the left-hand side, we'll only have Fd. And on the right-hand side, we'll have the degree D part, and so capital F is homogeneous, but G is maybe not. So we get all of F, and here the part of G that has degree D minus deg F. And so that is exactly the degree D part on the right-hand side. And in particular, that's something that's a multiple of F. And that means that FD is 0 in S of F. And that exactly means that the sum is direct. So in that sense, it's a nice decomposition of this S of F in the same way as in the non-graded case, the polynomials, the space of all polynomials, K and Q variables is a direct sum of the degree D parts. The same is true here. So that is the, first of all, the coordinate ring, but it's just that, so these elements are not functions now on F, but we can make it into functions by taking quotients of two elements of the same degree. And that's the first construction with that. And we want to get, in the same way as before, fields of rational functions, local rings, and all that. So that works as follows. So say that F is now a projective curve. So as before, irreducible over an algebraically closed field. So that was always our general assumption. And then part A, so we define the field of rational functions on F is, so the notation will again be K of F. And that is now again quotients of two elements F over G, where F and G are in S D of F. So that means they need both be homogeneous and of the same degree, actually. So F and G in S D of F for D and N. And of course, G is not equal to 0. And we consider that as a subring of the field of rational functions, of the quotient field of S of F. So that means we now take quotients of these homogeneous things of the same degree. And these are in principle things that you could evaluate at a point unless the denominator is 0, right? So that would be well defined. That would be well defined functions. So that means we can now make the local rings out of that. So that's B. So for P and F, to define the local ring, or the ring of regular functions at P. So notation is also as before, so it's OF comma P. And that would be the subspace here, so F over G in K of F, such that G of P is not equal to 0, so that we can write it in that way as before. So that will be actually a sub-ring here of K of F. And it means that for the elements of these ring, we will have an evaluation map at the point P at least, that's then well defined, and that goes to the ground field. And the kernel of that will be an ideal. And that's all very analogous then to the affine case. So just the construction to start with is different. Maybe that we need homogeneous polynomials of the same degree, but like the local rings, as we'll see in a minute, are actually also isomorphic to that in the affine case. So that's this one. And then see. So we have an evaluation homomorphism. So ring homomorphism from OFP to the ground field, maybe where phi goes to phi of P. And so with kernel, which we call again if comma p. Right, so it's just the kernel. So say all phi of O of p, such that phi of p is 0. And we can also write it, of course, in that notation here. So that will be all f over g in k of f, such that f of p is 0, and of course g of p is not equal to 0. So that's very similar in the type of construction. And also, we just do that simultaneously because it's also very similar. We can, all of these elements, so of both of the elements of the coordinate ring and also of the elements of the rational functions, we can define multiplicities at points. So the next part of the next construction is multiplicities. So again, say let f be a projective curve, and say P is a point in F. Then if we start out with the polynomial case, then for any homogeneous little f in S of f, we set the multiplicity, so we also denote this mu p of f. That should be the multiplicity in the old sense at the point P of capital F and little f. And that was by definition the dimension of the local ring of the projective plane at the point, which we call P2, P of P2, P modulo the idea generated by capital F and little f. So that's again pretty much the same definition as in the affine case where we had the affine local ring on that part. And then also as expected, so for any rational function, so phi in S of f, that we can then write as phi as f over g. We set the multiplicity of phi is just the multiplicity of f minus the multiplicity of g. And as in the affine case, it's easy then to see, I mean, we show it exactly in the same way. I don't want to repeat it. First of all, that this is well defined in the sense that, well, S of f is, after all, it's an equivalence class of polynomials. And it doesn't matter which class you take. And then here you have a choice how to write f, how to write phi as the quotient of two polynomials. Now, if we define mu p of phi as mu p of f minus mu p of g, then so one can check as in the affine case. That first of all, so mu p is well defined. And so meaning if I take a different representative here, I get the same result. If I take a different representative here, I get the same result. It's also additive, right? So that means mu p of f times g is mu p of f plus mu p of g, in the same way here. So mu p of phi times psi is mu p of phi plus mu p of psi. Additive. So in the case of rational function, that also means that we get a group homomorphism from the rational functions. So i.e. k of f star to the integers in the phi to mu p of phi is a group homomorphism. And also, which I probably have said earlier, that the result is infinite. So you have an infinite multiplicity only if f is actually the zero function or phi is the zero function. So that also we had in the affine case. So it's infinity only for f equals 0 or respectively phi equals 0. Because the infinite multiplicity can only occur if like little f actually shares a component with capital F, but capital F is irreducible. So it must be a multiple, but if it's a multiple of S, then it will be 0 in S of F. Right, so that's the same construction pretty much as in the affine case for the multiplicity. So you take the multiplicity of a function on the curve to be the multiplicity in the plane of the equation of the curve and the function. So that's the constructions that we did in the affine case. And to carry over the results, I mean, the first statement is actually that everything that's local here really carries over. So if we have, so for a point, let's say f a projective curve, and p a point on that curve, and say put it in the affine part, so of the form x0, y0, and 1, so in the affine part, a point on the curve, there's an isomorphism between the local ring in the affine and the projective case. Namely, there is an isomorphism from O of f and this point, so x0, y0, 1, to the inhomogeneous part, so we call this fi, and then at the point x0, y0. So that means the situation here is the projective one, and on the right here it's the affine one, and that is just given by dehomogenization. Right? So that means if I have an element in here which we can write as f over g, then we just dehomogenize that. So make f inhomogeneous, make g homogeneous. So that is easy to check, and that actually also takes the ideal I of f comma this point to I of fi comma that point. So it maps the capital I to the capital I, and that means that the properties, all the properties of these local rings are actually still the same. So for example, as we've just seen, that this is a discrete valuation ring, in the affine case will hold in the projective case as well, because it's simply the same ring. That should also not be surprising, because the local ring at a point should not care about if we add some point at infinity far away. So there's an isomorphism like this, taking in particular the ideal I f and this point x0, y0, 1 to I f inhomogeneous, and then x0, comma y0, and that means the local properties, or the properties, say the algebraic properties of the local rings, are the same. So, for example, also in the projective case, our O, Fp are discrete valuation rings. In the sense that we started out today's lecture. So that's still, I mean, it's still the same rings. Yeah. So, yeah, so I guess that's pretty much it, right? So that was carrying over the affine situation to the projective situation. Are there questions here? So then there's one concept that's really nice for bookkeeping all these multiplicities. So that is something we could have done this also in the affine case, but we are actually only interested in the projective case. So let's start it only now, and that is so-called divisors. Now consider so-called divisors. So this divisor, this notion of divisor has nothing to do with like elements of a ring dividing one in another. It's just like a totally different term. Actually, in German, the word is actually different. So that would be a divisor and not Teiler. So it's completely unrelated. So what these divisors are, it's a way, convenient way for bookkeeping multiplicities at various points. So that means not only consider one point at a time, but all points simultaneously. And so let's just start with the definition of divisors. So say let f be a projective curve. Then we don't need a point for that, but we would say like a divisor on the curve is just a formal finite linear combination of the points of the curve with integer coefficients. So a divisor on F is a formal finite linear combination of the form, so A1, E1 plus and so on, A and Pn with, so n is a natural number, so a certain number of points. Then all the Ai are integers, so in Z, and the P1 up to Pn are points on the curve. So another way of saying that is, so in case you know that, it would be the free abelian group on the points of the curve. So if not, then it's just noting that these objects here obviously form a group under addition, under formal addition. And this group will be called the group of divisors. And we'll write this as div F. So that is a divisor. So these divisors form a group under formal addition. And we denote this by div F. So if you know this, so in other words, you know this terminology, so div F is the free abelian group on the points of F. For that an abelian group, just take all the points and allow formal linear combinations of them. There's two more notations for these things. Namely, first of all, there's a partial order on this thing, namely as follows. So we say a divisor. We'll often denote this by a letter capital D. So as up there, so A1, P1 plus and so on, A and Pn is called effective. And the notation for that is one writes D greater or equal to 0. If all entries are greater or equal to 0, so if AI greater or equal to 0 for all I. Effective just means no negative coefficient. And we can use that to also compare two divisors, at least in some cases. So for D1, D2 divisors, so in div F, we write D1 less than or equal D2 or D2 minus D1 effective for this greater or equal to 0. So that defines a partial order on div F, which means that one divisor is less than or equal another if for every point the coefficient in the first is less than or equal the coefficient in the second. Defines a partial order on div f. And one last piece of terminology, which is quite natural, is such a divisor has a degree, and the degree is just the sum of the coefficients. So in a sense, it's the number of points counted with multiplicity contained in that divisor. So you should think of that divisor here as containing the point pi with multiplicity ai. The degree of such a divisor, so of d a1 p1 plus and so on a and pn, is defined as, so we also write this deg d, and it's just the sum of all those numbers, so a1 up to an, and that's of course an integer. So essentially just taking the sum as before, like the formal sum, and forgetting all the points, just adding the coefficients. And I guess it's clear then from the construction that this degree is a homomorphism, right? So as the group here is the additive group on these formal sums, and in Z also we have the addition, so that means note that this degree map is actually a group homomorphism from div f to the integers. Right, so that's a divisor, finite formal linear combination of that type. So the reason why that is important, you might already guess, is now that if you have now a function, like be it a polynomial or a rational function, so a quotient of two polynomials, we can form a divisor from that by just summing over all points of the curve and assigning to those points the multiplicities that the function has at this point. That's now the construction that is basically the motivation why we consider divisors at all. Namely, we can get divisors from polynomials or regular functions. Let's do it in those two steps. So, but in any case, let f be a projective curve. Then part A, again, as we did it for multiplicities before, if we have a homogeneous element of S of f, so if, say, little f in SD of f is non-zero, homogeneous of degree d, we said the divisor of f, so we write this as div f, so pronounced like divisor of f. And that is the formal sum over all points on the curve, and then you take the multiplicity, mu p of f, times the point p, where this is like the formal sum in the definition of divisors. So that here is the formal sum. And note that any polynomial, of course, will have only finitely many points where this multiplicity is non-zero. So although it looks like an infinite sum, it's actually a finite sum. So this is a finite sum, since f, has only finitely many zeros. So and in that sense, like this one divisor, this one algebraic object captures all the intersection multiplicities, all the multiplicities of the functions at once with that curve. Of course, the same thing we can do with a rational function. Here we can actually note, so if we do it with a polynomial, then these multiplicities will all be greater or equal to 0. So it means that will be an effective divisor in that notion. Note this divisor is always effective. Right? So the coefficients can never be negative, but that changes if we have a rational function, of course. So b, if phi, which we can write as f over g, is a rational function and not the zero function. So in kf star, we said with the same notation, so we would write div phi, and that's defined as, again, the formal difference, so divisor of f minus the divisor of g. Or another way of saying this is to say it's the sum, again, over all points p and f, and then we take the multiplicity of phi at the point p times p. So that's not effective in general anymore because there's a minus here, so we can have negative coefficients. Maybe we just consider one example to make this clear. And that's very close to one of the examples that we had last time. Namely, we consider the curve f to be y squared plus yz plus x squared. So we had this as an affine curve last time, which was then without the z. And we saw that it was the curve that in the affine part, and the real picture of that looked like this. So that was the circle here that touches with a horizontal tangent the origin. And we had computed of a certain rational function, namely for phi, which was y over x. We had computed there that if we consider the 0 point here, then y has a double zero at this point, x has a single zero at the point, and so the whole function had order 1 at this point. Right, so from last time, we know already, so at the point 0, which now in the projective case would be the point 0, 0, 1. So like the z coordinate is 1 and x and y are 0. Multiplicity of y is 2, so point 0, 0, 1. And the multiplicity at the point 0, 0, 1 of the function x was 1. Well, that's just in the picture, right? So y is the tangent to f at this point, but x is not. So this has multiplicity 2, this has multiplicity 1. And that means that the multiplicity at the point 0, 0, 1 of that function phi was 2 minus 1, which is 1. So now what we do different is that we not only consider the origin, but we consider all the points. And so if we consider all the points, then what happens? So y still has only this origin as the 0. So that is y here. And that meets f only at the origin at this one point. But x has one more intersection point. So this is x. And that intersects the curve in one more point down there. Right? And that means that the divisor contains one more contribution. Oh, and moreover, so x has one more 0 on f, which you can probably see, right? So if we set x equal to 0, then the remaining equation is y squared plus yz equals 0. Write this down. So y squared plus yz plus x squared and x is 0 means that the first two terms, which is y times y plus z and x are 0. And that has two solutions. Either y is 0 as well, that's still the origin, or we have y plus z is 0. So that means we have the additional point where x is 0 and y plus 0, 0, so 1 minus 1. All right, so that's the point down here. That would be, or write it the other way around, maybe it's better, minus 1 plus 1, so that's the point. 0 minus 1, 1, right? Which again is in the affine part, the point 0 minus 1. And the multiplicity with that is 1. We just compute it in the same way as in the affine case. You can see it here. I mean, it's the transverse intersection, right, of the curve with x. So that means we have a multiplicity of 1 for x and of 0 for y. And that means that our rational function phi at this point has multiplicity 0 minus 1. So that's a minus 1. Well, it means we have a simple pole in the terms that we introduced last time. So that means at this point, so 0 minus 1, 1 of the function, what was it, x is 1, whereas the multiplicity at this point of y is 0. And that means that the multiplicity at this point of the rational function phi is the difference. It was y over x, so it's 0 minus 1, so it's minus 1. So in particular, what this means now for this rational function, we know that it has a non-zero multiplicity only at 2 points, namely at this point and at that point. And here it has order 1, and here it has order minus 1. And so if we form the divisor, then we just set these things together. So the divisor of phi will be 1 times the point of the origin, so 0, 0, 1, plus, and then minus 1 times the point 0, minus 1, 1. Right? So it's a formal combination of 2 points. That would be a divisor, an example for that. Yeah. So first, everything that's sort of additive now for multiplicities will just transfer to divisors. Right? For example, the additivity of multiplicities just translates into an additivity of divisors. So the idea is really just to make things simpler here, to consider all points at once. So remark that is like additivity of divisors. Again, for a projective curve, capital F, first of all, say for little f homogeneous of degree d, or say f and g homogeneous, don't need a degree here. So f and g homogeneous in SF, I should say. We get that the divisor of f times g, so of the product of the two functions, would be, well, by definition, it is we sum over all the points, p and f, and then we take the multiplicity of f times g times the point. But the multiplicity is additive, and hence we can write this as a sum f p and f, mu p of f plus mu p of g times p, and that's of course the divisor of f plus the divisor of g. And in the same way that works for rational functions, so if I have two rational functions, f and phi and psi, then the divisor of phi times psi will be the divisor of phi plus the divisor of psi. And again, as before, for the multiplicity at a point, this means that this divisor map, so this map div here, is a group homomorphism from the multiplicative group of rational functions without zero to the group of divisors. So in the same way as before, so second part, analogously, for phi and psi, rational functions not zero, we have that the divisor of phi times psi is the divisor of phi plus the divisor of phi, i.e. so this map div going from kf star to div f is a group homomorphism. So there's more things that we can carry over actually. So it's just, there was just multiplicities carried over. And two other things that we had for projective curve, namely Bezout's theorem and also like Max-Noether's theorem, have nice interpretations or rewritings in terms of divisors. Let's do this as well. It's really just remarks. I mean, it's quite obvious and immediate. So let's start with Bezout's theorem for divisors. That would tell you what the degree of such a divisor is. Then if we have a projective curve, so let F be a projective curve. And in part A, say as before, let F be a homogeneous polynomial of degree D. Okay. Of degree D, and say F is not 0 in SF, so it's not a multiple of F. Then we can say what the degree is of the divisor of F. Namely, by definition, that is, so the divisor, let's write it like that. First of all, it's the degree of this divisor, which was the sum over all points, and then mu p of F times P, and the degree just collects the coefficients. So that means we get a sum over all points P and F of the mu P of F. And that was defined to be the multiplicities in the projective plane of capital F with little f. So we sum up all these multiplicities, and Bezout's theorem told us what we get from that, namely the product of the degrees. So of the degree of the curve and the degree of the polynomial that we consider. So of capital F and little f. So that is by definition of these multiplicities, the sums over all P and F, and then mu P of F, capital F, little f, and thus by Bezout is just the degree of capital F times the degree of little f. So we know what the degree will be of this divisor, and it's even simpler for rational functions. So for phi, a rational function which is non-zero, so we can write this as f over g, with f and g homogeneous of the same degree. And that means that if we take the degree of the divisor of phi, then the degree was the homomorphism, so we can write this as the degree of the divisor of f minus the degree of the divisor of g. And both of them by part A give the degree of f times the degree of little f or little g, but that's the same. So we get just 0 here. Take f times take f minus capital F times big G, and as those numbers here are the same, we just get 0. So that means a divisor of a rational function always has degree 0, right? So we have this in the example up here. We had 1 times something plus minus 1 times something. Or in other more geometric terms, a rational function always has as many zeros as it has poles, if we count them with multiplicities. Right. So that's for Bezout's theorem. And then we have, like in the same chapter, Max-Noether's theorem as well. And that also has a translation into the language of divisors where it looks a little nicer. So I formulated here as a proposition, but it is pretty much a corollary of the old Noether's theorem. So what does that say? No propositions. Noether's theorem for divisors. And that says the following. So I'll say first again, let F be a projective curve. Now, Max Noether's theorem always needed it's a smooth one, but we have this as a general assumption anyway. So let F be a projective curve, smooth and irreducible, of an algebraically closed field. And there we have two polynomials, G and H, homogeneous in S of F, such that the divisor of, say, G is less than or equal to the divisor of H. So in the partial order on divisor. So what that means is, of course, that the order, the multiplicity of G at every point is less than or equal to the multiplicity of H at the same point. So the statement is, so then there is a B, and that was corresponding notation as when we had Max Noether back directly. So then there is B and S, then there is B and S of F also homogeneous. In fact, of the degree, the difference of the two. So of degree dec H minus dec G. Such that H is B times G in S of F. And hence, for the divisors, this means that the difference in the divisors also is made up by B, so div G plus div B is div H. So that's the statement here, right? So we have two homogeneous polynomials, and at every point, the order, the multiplicity of the one is less than or equal to the order of the other, and then the remaining parts of the divisor can be obtained from intersecting with another curve, or like as the multiplicities of another polynomial. And so in the proof, we actually see that this is nothing but the old theorem. It's just a reformulation, because the assumption here just means the assumption div G less than or equal div H means, by definition of this partial order, that the multiplicity, so mu p of G, is less than mu p of H at every point P and F. And this multiplicity was defined as the multiplicity of capital F with G. And that's the same as the multiplicity of capital F with H. And that was exactly the assumption for the old Noether's theorem. So that we have two polynomials, G and H, such that at each point, this multiplicity is less than or equal to that multiplicity. And the statement of old Max Noether was that then we can write H as AF plus BG for some homogeneous polynomials. So then by the old Max Noether's theorem, we have that, or H is A times F plus B times G. So F, capital F is the curve, so I write it with a capital letter, and the others are our given polynomials. And this holds then as polynomials That was exactly the statement of Max-Noether's theorem. And if we pass to S of f to the quotient ring modulo f, this means that H is B times G in S of f, which is precisely that statement. And then the additivity of divisors just gives the statement of divisors. So I guess you see it's really just, I called it again proposition, but it's maybe pretty much also a remark. It's just directly translating Max-Noether into the language of divisors. Yeah. Any questions? So there's one interesting corollary from that, really. Namely, earlier today, we considered what are the regular functions, the global regular functions on an affine curve. So we could, in the same way, ask what are the global regular functions on a projective curve? What would we expect? So, I mean, from the affine case, we saw that it's really just polynomials. I mean, you cannot have anything in the denominator, but polynomials are not functions. I mean, not well-defined functions on a projective curve, unless they are constants. And that is, in fact, the result here. So, for any projective curve, F, we have that we write down the same as before. We intersect all points on the curve, and then the local ring considered as a subset of K of F, and so this would be like the global regular functions, so regular functions at every point on F. Then these are just the constants, and that means it's the ground field K sitting as constant functions inside Kf. But it is similarly easy to imagine that this should hold true because, well, I mean, we need quotients of polynomials of the same degree, but if we actually had a denominator, then the denominator would vanish somewhere, and that would give a point where we had poles. That's not allowed for regular functions. So that means we cannot have a denominator, and so as the degrees are the same, we also cannot have a numerator, and then we just have constants. By the way, the reason why this is not just the complete argument and why it's not a trivial statement that this is true is exactly this thing that we don't have factorial rings here, right? So that means there's no uniquely determined way to write such a phi in the intersection as f over g. It might be that we need different f's and g for various points that are just completely unrelated. And so that means this argument by saying, well, take this g and that must have a zero somewhere is not an argument, because it might be at the other point you have a different representation with a different denominator, and then maybe it might be well defined. So that's just the intuition behind that. But an exact way to prove this is, for example, given by Max-Noether's theorem. So let's take an element in there. So say let phi, say take one representation here. So write it in one way as f over g. In K of f be a globally regular function. Then what this means is that it doesn't have, as a rational function, it doesn't have poles. Right? So that means for any point, P in F, the multiplicity of phi must be greater or equal to 0. That just means regular at that point. And the multiplicity is just the multiplicity of f minus the multiplicity of g. And that is greater or equal to 0. And so that means, in other words, mu p of g is less than mu p of f for all points. And that we can reformulate in terms of divisors, namely the divisor of g is less than the divisor of f. So that just means it's regular at every point. So then we have here Max-Nutter's theorem, which tells us we're now in exactly that situation. We have a projective curve, and the divisor of one polynomial is less than or equal to the divisor of the other, and that means that the remaining part must be made of by another polynomial. But this polynomial has the degree like the difference of the degrees, but f and g have the same degree. So that means actually we must have that f is g times a constant polynomial. So by Max-Noether, this implies that f is some, we call the b there, times g for some polynomial of degree like the difference of the degrees. So deg f minus deg g. So that is 0, right? As we always have a quotient of polynomials of the same degree. And so that means b is a constant. And that means phi, which is f over g, is this b, and is a constant. Right? So that is already, I mean, that clearly is a non-trivial statement, although it's an expected statement. Probably we need some work to show that. Right? And so that tells us in both cases, so both for the affine and for the projective curves, what the global regular functions are, namely just the polynomials, respectively just the constants. There's one actually quite interesting remark that follows from that is maybe unexpected, namely that the divisor of a rational function pretty much determines the rational function back, which sounds a bit weird maybe because the function sounds like a more complicated object than just a couple of points with multiplicities, but actually that is true. So there's a way to recover irrational functions from their divisors. And that is the following statement. So let's say, so let phi be a rational function, say non-zero, with divisor div phi. And here we have another rational function which has the same divisor. And say psi, another rational function with the same divisor, div psi equal to div phi. What does that mean? So that means that if I take the quotient divisor of phi over psi, that's still a rational function, is the difference of the two, which is 0. So is the phi minus the psi, which is 0. And in particular, it contains every point with a non-negative multiplicity, and that means this is a regular function. So in particular, phi over psi is a global regular function. It has no poles anywhere. In fact, it also doesn't have zeros anywhere. But the global regular functions are just constants. So by the corollary, Following, yeah. This means that phi over psi is a constant. And hence that one is just a scalar multiple of the other. So that means if we know the divisor of a function, that actually determines the function up to a unit. Hence, knowing the divisor of a rational function determines phi up to a multiplicative constant. Okay, so that maybe sounds surprising at first. So like a couple of points with multiplicities is sufficient on a projective curve to determine the whole function. I mean, not every combination of points will be the divisor of a function, but if I have a divisor that I know is one, then the function is pretty much unique. Yeah. That's this remark. So that's just this, as I say, like a more convenient way to compute with all intersection multiplicities at once. The problem with that now again is that this divisor group, I mean, from an algebraic, so from a group theoretic point of view, is really big, right? So it's a free abelian group with probably infinite, well, not probably, I mean, we are on an algebraically closed field, so the curve has infinitely many points, so that means it's a free abelian group on infinitely many generators. So that's from an algebraic point of view not really a very nice group to work with. I mean, it's just really big, like the problem, so to say. The group div f is huge. So, and one way around this is to make it in a more tractable group is to take a quotient of that group by something that is sort of trivial to mod out, and then to obtain smaller groups that we can easily work with. And that is the following definition. And these are then the groups that are actually a little more important than the divisor groups, namely the so-called divisor class groups, or Picard groups. Namely, we want to mod out a subgroup essentially from that. And that is the subgroup of so-called principal divisors. And a principal divisor, we know this already, this concept is just a divisor of a rational function. Of course, in general, as usual, so let f be a projective curve. Then part A, we say a divisor in div f of the form div phi, or phi a rational function which is not zero, is called principal. And the set of all these principal divisors we'll call prin f here, so for principal. We know the set of all principal divisors by prin f. That is actually a group because we had already seen that the divisor map is a group homomorphism from Kf star to div f, and so this is just the image group, right? So that's another way of saying that. So it is a subgroup of div f, namely the image of the divisor map from kf star to div f. So that is a subgroup. In fact, we have also already seen that these divisors of these principal divisors, or divisors of rational functions, always have degree 0 as the consequence of Bézout's theorem. And hence, there's a refined version of that in a sense, namely that this printf is not just a subgroup of div f, but also of the subgroup of divisors of degree 0. So, moreover, as the degree of the divisor of phi is 0 by Bézout for all phi and kf star, we have that this printf is also a subgroup of, usually then denoted div 0f, and div upper 0 of f is defined to be the set of all, or the subgroup of all divisors of div f, such that the degree of the divisor is 0. So sometimes one uses div f, sometimes if 0f, just what one is more interested in. And the idea is now just to take the quotient of these two groups. So that means you take the divisors or the divisors of degree 0 only, depending on what you're interested in, and then mod out these principal divisors. So that's B. So the quotient group and that we denote pic for Picard group. Pic f is defined to be div f modulo printf. Is called Picard group of f, or just group of divisor classes, or in the same as we have an equivalence relation and take classes modulo this relation. So sometimes these are just called divisor classes. Of course, one can do that in the same way for the degree 0 part. So alternatively, we set take 0f to be div 0f modulo printf. So if we are only interested in divisors of degree 0 to start with, we can also do this for divisors 0 to start with. So, but we'll see next time, and probably this contains pretty much the same information. So sometimes we take this group and sometimes we take that group. And just one more piece of relation. So that is just of notation. That is just an equivalence relation here, of course. And if two divisors are equivalent, so if D1 and D2 are divisors with the same class in the Picard group, in pic f, then these divisors would be called linearly equivalent. Now, so that D1 and D2 are called linearly equivalent. And this is written by the usual equivalence relation symbol. So with that tilde D1 over D2. So and these are then the groups. So the time is up now, so we should stop for today. But these, as we will see, are very nice groups then. So they are usually quite small for a curve. So they are more easily tractable, and we'll just study these groups then next time. Yes. So no more questions. Then stop here for today. Continue that next time. Right? Okay.